loud and clear. How's it going?
Not too bad. I saw a video the other day where this guy claimed to get a COP of 30 from a Peltier bank. Do you think that's a realistic kind of amount? I think he said he got 30 watts of cooling with just 1 watt input. Is it junk science or credible?
Yeah, that definitely sounds a bit too good to be true. Typically, Peltier modules have a coefficient of performance, or COP, that's well below 1. Usually it's around 0.5 to 0.8 or so, meaning you get less cooling power than the electrical power you put in. So a COP of 30 would be extremely unrealistic. It's probably some exaggeration or misunderstanding.
G'day everyone, my name's Peter Selby and I've been wanting to make a video on this guy behind me. It's a GS, I don't know, it's a geothermal, solar powered, Peltier based air conditioning system. And in the introduction to that video, I threw out a kind of shock value number where I measured a COP of 30. Now COP, if you don't know, is a ratio of the cooling power divided by the electrical power going into the Peltiers. In this case, it was 30 watts coming out of the system with only 1 watt going in, so that ratio of 30 there. Now the number was meant to be a shock value for the audience, but it kind of backfired, and I realized that, do I actually understand exactly what's going on inside the heart of a Peltier device? So I went down this rabbit hole. While I was down there, there was a whole bunch of other stuff that I discovered, like for example, heat pumps are meant to be pushing against a temperature difference, but what happens if there's no temperature difference there? Do they still work, or maybe even a negative temperature difference? There's a Carnot cycle which predicts that when you get to a DT of 0, it's an infinite amount of COPs. What does that mean? And it gives negative COPs if you're going into the negative DT world. Couldn't understand that. There was a fence post problem as well. A whole bunch of stuff that was all floating around. But eventually I figured it all out, and I just thought I want to make a video on that stuff rather than the air conditioner, which I will come back to. But I thought, hey, let's just make a video on that COP of 30 and what it helped me understand. So hope you enjoy it. Okay, before we start, I do need to do a few housekeeping things here. I think the first is this COP of 30 as well as the DT of 0. That's going to spin a few people out. There's going to be a lot of skepticism there. I think the best way to deal with that is just to put it to one side and wait till you see all the material. And also keep in mind that the COP of 30 it's a very special condition, so it's not kind of real world stuff. It's more of a gateway to explore how Peltiers work, just the magic of the Peltier function. The second thing is that I've been playing around with this video for probably more than 2 months now. I just keep reorganizing the material. I keep re-recording me talking because I'm not very good at it. And then I learn new stuff as I'm making the video. So it all keeps just jumbling it all up. I'm going to split it into 2 parts as well. It's a bit hard to keep it into, say, 30-minute video. So the first part will be talking about the theory, the current theory, and the second part will be explaining some of the, let's say, misconceptions as well as the counterintuitive stuff from that theory. So this particular video, I'm going to introduce the air conditioner first. I think it's a great illustration of some of the points that I'll be making. Next, I want to introduce a simple circuit-based model for how Peltiers work, a thermal circuit. Then I want to show kind of cool experiment here using a couple of aluminium blocks with a Peltier in between it. So that'll help to illustrate some of the circuit that I'm talking about, as well as some of the concepts. And then I want to go into some of the formulas. And the good thing is that having looked at that model as well as the experimental stuff, the formulas hopefully will not be just this jumble of characters on the screen. You'll be able to see a bit of color and difference of what all those different parts mean, even though the formulas themselves altogether are a little bit dense, so to speak. At the end of all that, I'm just going to summarize what I think are the main sort of problems and misconceptions about Peltiers that come from that theory. And to be clear, I do not want to, let's say, counteract any of the existing theory. So Lord Kelvin is not rolling over in his grave. The Carnot theory is fine. The ZT theory is all okay. Second law of thermodynamics, the conservation of energy, the equations that apply to Peltiers, as well as data sheets for Peltiers. Absolutely nothing that I'm trying to challenge here. I'm not trying to do a bit of alchemy, but rather there are some definite misunderstandings when people interpret the results out of that theory. And there's also some really weird counterintuitive stuff in there. So I'm going to leave all of that to the second video to sort of unravel all of that mess and hopefully provide a good explanation. All right, so with that, we'll kick on to the first thing, which is going to be explaining how this system works in a very brief way. Okay, so it's time to introduce my baby here. This is the Peltier-based air conditioning system, and it has a few secrets in there. The first is that the bank itself has 10 Peltiers in there, and the reason for that is you don't want to drive these guys too hard on their own. Individual Peltiers, probably about 30 watts of cooling would be the good sweet spot for decent amount of cooling, still getting a decent COP, as well as can handle a bit of DT without sort of fluctuating too much. So if you're getting 30 watts from here, I can get 300 watts of cooling from this bank, or maybe 4 to 450 watts of heating depending on the conditions. The second secret for this is a very low thermal resistance heat exchange on the top here. It's just made up of these kind of gamer PC water to air heat exchangers. Just a single fan, so there's 4 of those arranged in a box there, and then just a single fan out the end seems to work quite well. On the floor side here, on the geothermal side, I actually have a kids pool. It's 220 litres there, and it acts as a thermal ballast, but it's also sitting on the cement foundations there, and that's picking up the heat or the milder temperatures in that environment there, which helps to keep the DT much narrower between the hot side and the cold side for the Peltier system, which is very important for efficiency. There are, of course, the peripherals here. You have the cooling fan. There's 2 aquarium pumps, one on each side, so that adds up to about 14 watts for the system. And then the latest addition is a little monitor system here. I've just co-opted one of my other designs there and use that to monitor, like a standalone monitor for the system. So I've taken a few photos there. I think one was running off the solar panel, so I think around, 32 volts or something from the panel. And you can see there, I think it was getting 410 watts, maybe a system level COP with the fans and pumps and everything included. It was a COP of 2.7, I think. And then I also took another photo with it running off the just a battery that I use for nighttime use. So it's only drawing 35 watts, including pumps and stuff like that, but still getting 130 watts of heating. And that's enough to keep the room at a stable temperature at nighttime. If you have proper closed off windows and stuff like that, it seems to be enough. So that's basically the system. So where did this COP of 30 come from? Well, if I'm going to be comparing different designs, so I've got this like an old style cell here for just a single Peltier. Some of the cooler designs I've got now, which I'll be talking about in future videos, or just let's say Peltier banks, multiple Peltiers. This is an old style one here that I was using last winter. This guy over here is like my crazy V12 system. There's way too much plumbing in there. So there's 12 Peltiers in there, but I think there's just too much path there for the water to push through, which was killing the efficiency of this guy. And then, of course, this guy here. If I want to compare all of those designs under a good condition for comparing stuff, I want to set up a DT of 0. So this is not saying a DT of 0 is representative of real world conditions, but it's just a great condition for comparing one design against another. And so when I was doing the test on this guy here, at first, if you drive it hard, I forget the number, whether it was maybe 2 amps per cell, then I was getting a COP of around somewhere in order of 2. You'll see it on the diagram there. But if I started reducing the current down, you see this 1 on X kind of shape for the COP. So I went down all the way down to 1/4 of an amp per cell. And for that, I was getting a COP of nearly 24. So I went one step further and thought, okay, I'll just power it off a couple of AA batteries for fun. And I got this COP of 30. So it was 30 watts of cooling for less than 1 watt going into the Peltier bank. Now, I've since recreated that condition with the new meter and using a proper power supply rather than the batteries. And I still got a COP of 30. I think it was around 40 watts of cooling with 1.4 watts going into the Peltier bank. Now, of course, if you add in peripherals, that's going to really kill the COP. I think it drops down to 2. You could argue whether that's makes sense because these peripherals are being driven really hard, so I could back them off quite a lot. But anyway, that's beyond the point. The main thing is that I was getting these incredible COPs out of just the Peltier bank itself, but it's following this 1 on X kind of curve there, which is actually predicted by the data sheets themselves. Now, I did want to just, last point was to just show you those, the figures that I measured for the whole system, and then I want to overlay the datasheet values. And you'll see I'm only getting about 70% of what the data sheet says anyway. So I'm not doing any kind of alchemy here that gets more out of the Peltier than what the manufacturers say. It is all legit kind of stuff. Okay, so that's the story of the system as well as where that COP of 30 came from. Next, I'm going to go on to the modeling for an individual Peltier. Okay, it's time to get into the classroom here, but don't worry, the circuit itself, I'll put it up on the screen, is not too complicated. There's only 3 components in there, but before I explain those, I do need to explain thermal circuits. So what we're doing is to borrow symbols from the electrical world to represent things in the thermal world. And we can do that because of a similarity between some of the relationships between things like voltage, current, and resistance, and temperature, thermal resistance, and heat flow have a similar kind of relationship. So to illustrate that, I'm going to go to just a simple Y here. Let's say I put 10 amps current through here and I measure 1 volt difference from one side to the other. I can derive that the resistance of this circuit is going to be 0.1 ohm. So hopefully that should be obvious for the listeners. If I did something similar in the thermal world, maybe I've got a resistor here that's pumping out 10 watts. I keep the other end here grounded with maybe a water circuit here to keep it at ambient temperature. So maybe the temperature of this side goes up by 1 degree. I can then derive from that I have 0.1 Kelvin per watt resistance, thermal resistance in this circuit. So that's basically how we can borrow those kind of symbols or those concepts. Don't go too far with it. It's just use that basic linear relationship, but don't do things like I squared R. You'll get all confused about that. And also keep in mind for a Peltier, it's got thermal stuff here and it's also got electrical stuff here. So sometimes you'll have to keep on your toes to figure out which one of those I'm talking about. All right, so with that, I can start to talk about the actual circuit itself, and I'm going to rip it apart. So to start off with just that core heat pump effect in the middle, which is, we use the symbol for a current source in there, which is a heat source in the thermal world. And this is a wonderful effect where it's proportional to the current that's going through the Peltier itself. So for a typical Peltier, a 12708, this guy here, it's around 20 watts per amp. So 1 amp through here will create 20 watts of cooling or 20 watts of heat pump effect. 2 amps would be 40 watts, 3 amps 60, half an amp 0.5, half an amp will be 10 watts. Okay, so it's a pretty cool effect. The other thing is you can reverse it. If you put the current through the other way, the hot and cold sides will reverse and the whole thing just works exactly the same. And the other thing is that with this kind of source, it's really a floating source here. It's different to a normal heat source, which can only put heat into the environment. And for the thermal circuits, we always represent this as having one leg in the ground or a grounded side. And that's because the heat can only flow into the rest of the circuit. It can't create negative temperatures. Whereas this guy here, we can put this in the circuit wherever we like, and including creating negative temperatures in there, which is why we love them for heat pumps. All right, so that's the good stuff. Everything is downhill from here. The first really big negative effect is just this leakage resistance. You can see there's not much space there between the hot and cold sides, and it's a conductor inside there. So you can imagine the heat is going to easily flow back from the hot side to the cold side. And typical Peltier like this is about 1 Kelvin per watt. So imagine we've got a can of beer that's at 5 degrees and our room temperature is 25 degrees. Then you're going to get about 20 watts of backflow heat that's working against the main heat pump effect. And let's say we only need 3 watts to keep the can at its cold temperature, but we're going to need to run this guy at 23 watts in order to get that 3 watts out at the end. So it's not a very good situation, and you can kind of see why Peltiers just aren't very efficient. Now the other bad thing about Peltiers is that you have just normal I squared R losses. So it acts like a resistor. You put a current through here, you will get I squared R losses, and they will have to somehow flow through the system, and they usually make things worse. So for the model, I found the best way to do that is to take that internal thermal resistance, that 1 Kelvin per watt, split it into 2 parts, so 0.5 and 0.5, and you have a grounded heat source, because it is just a normal heat source, and that pops up in the middle there and connects to the midpoint between those two thermal resistances. And that model, that's basically the end of the model. It works fantastic. I use that model or similar versions of it to predict the performance of my systems, and it all matches very well. There's one more negative effect, which is the Seebeck effect, and it comes about because when you have a temperature difference from one side to the other, it creates a voltage here which generally the current has to fight against. So that makes the apparent resistor appear a bit higher. Don't want to go too much into detail about it at the moment, but just be aware that the power input will be a bit higher than what you would predict from just the basic resistance. So for example, this guy here should have a resistance of about 5.9 ohms, but in practice it normally reads about 7.5, maybe 8 ohms, and that's because of that Seebeck effect. So if you're going to measure the COP, you do need to take that into account, because it makes your input power higher than what you would predict based on the resistance only. Okay, so that's the end of the description. There is one more thing I wanted to say about this, is what the experts say is that if you wanted to improve the performance of a Peltier, we need to increase the thermal resistance, but unfortunately that also increases the electrical resistance, so you get higher I²R losses. So you get this whack-a-mole kind of effect, that you're trying to fix something over here and then you just make it worse over here. So basically it's a game over situation that you can never win. All right, so that's the model of the Peltier. We'll move on to next the experiment, which is going to illustrate some of those effects in a pretty cool way, at least in my opinion. Leave it there. So it's time to get into the laboratory. So I've got an experiment here. It has a couple of aluminium blocks here. They're 40 by 40 by 40, and they're sandwiched around a Peltier there in the middle. There's a little bit of thermal paste in there. The most important thing is this clamping action that I've got going on here to keep the thermal resistance between the Peltier and the blocks down to as low as possible. Now the blocks themselves have a hole drilled in there, and I've got a medical grade sensor here that I can get right into the middle of the block. That sensor is then connected up to a very high resolution data acquisition system where I can derive temperatures of around or exactly 1 millikelvin or 1,000th of a degree. We'll see why we need that later. So the test itself has a few different phases. The first phase, just let it run for a minute to make sure that everything is stabilized and both temperatures are the same. Then I apply an AC pattern here. So I've got 345 milliamps in one direction, and then I'll flip that so I've got minus 345 milliamps in the other direction. And I'll do that really quickly at 1 kilohertz, so only 1 millisecond per phase there. The reason for that is I want to cancel out the Peltier effect, so that I've only got the I²R losses or the I²R effect that's remaining. So I'll be able to see that I²R should lift the temperature of both blocks by the same amount, and we'll be able to see that thermal imprint there and get a bit of information about that there. The next phase is just a minute to let it all rest again, just to make sure that nothing untoward is happening, and then I'm going to apply the Peltier phase, which is where instead of flipping the polarity around, just a single polarity of 345 milliamps. So exactly the same current, but just keeping it one polarity. And for that, we should expect to see the heat pump effect, this really wonderful heat pump effect, where we're literally taking heat from one block to the other block. So we'll see the temperature of one block go down and the temperature of the other block will go up. An important point important stop here is to remember a lot of people think that heat pumps can't work with a DT of 0. So this setup here, we have a DT of maybe 1 or 2 thousandths of a degree, and yet we are going to see a heat pump effect. So this really disproves that misconception that heat pumps need a DT to work against. So we'll let that run for another minute, and then we'll compare what kind of temperature deviation we get there between the two blocks to that I²R. That'll give us some indication of the COP of the system. Then I'm going to turn the power off and just let the temperatures reduce. So that's going to show us that terrible leakage that the Peltier itself has. So there's not much leakage outside the system here, but the leakage inside the Peltier there, the thermal resistance, is going to allow the temperature from the hot side to flow into the cold side. All right, so with all of that, let's go on to the actual test itself. I'm not going to run it real time. I'll just show you each of those phases and talk you through them. So the first phase there showing the both blocks are the same temperature and also very stable. So we'll run that for a minute, and then I'm going to apply that the AC test. So we do see a temperature rise here. It's about 51 millikelvin, not very much, but it's a clear indication there. And we can map that back to things like the thermal capacity of the aluminium blocks. We can calculate all that through and make sure as a double check that the numbers make sense, and they do make sense. So then we let it rest for the minute again. Now, before we start the actual Peltier here, what I want to do is to predict what's going to happen if we have a COP of 1. Now, the numbers are a little bit confusing because the first phase there, the heat, that I squared R heat, is being shared by both blocks. So we only see half of the I squared R in each individual block. So when we change it to a COP of 1, it ends up being that the cooling that we expect to see should be twice that rate, and the heating should be 3 times the rate. So the difference there being the I squared R is still in there in the mix. So I'll put the lines up on the screen anyway. Don't worry too much about the math. I'm also going to put a line up for what I expect if I have a COP of 10, and then we'll be able to compare the actual result for it. So let's roll tape and see what happens. Wow, just look at this. It's off the screen with just 5 seconds and we're off the screen there. We have to zoom out a bit and zoom out again, and then finally we can see the Peltier effect there. It's just so much bigger than the I squared R losses here, and that's because we're doing this test at a very, very low current. Now, actually, I didn't want to do this test at this particular current. Future editor here. The talking head there got some of the numbers wrong as well as missing a few key points, so I'm just recording the audio for this again. So I really want to contrast this, the AC bit versus the DC bit. This is the I squared R bit versus the Peltier bit. So to run some of the numbers there, the AC bit was run at plus or minus 345 milliamps. The actual power was measured at 290 milliwatts, and that produced 51 millikelvin temperature difference, all fairly small numbers there. Now the DC bit was also 345 milliamps. It produced also 290 milliwatts, but it produced 1,697 millikelvin temperature difference between the hot and cold side. So that's roughly 1.7 degrees and maybe 0.8 degrees worth of cooling. Still kind of small numbers, but the key point is the ratio to that the phase 2 there is quite massive. Now I can analyze the first part of that waveform there, the first say 10 to 15 seconds, and you can pull out a maximum QC of about 7 watts, which matches also the data sheets, the manufacturer's data sheets, and that clicks in at a COP of about 24. Now, despite or putting aside all the numbers there, what I really want to emphasize is the almost negligible I squared R losses. They're just more of a rounding error here, and yet we're still getting quite a significant Peltier effect, 7 watts. It's surprising for me, and I'm sure it's surprising for a lot of experts to see that there's still a significant amount of heat pump effect there. Okay, so now we want to move on to the next phase here, which is where we turn the power off, and we have that temperature difference there, and it's going to leak back through the Peltier there, through that leakage resistance, the thermal resistance, which we said before was around 1 Kelvin per watt. So I actually analyzed these curves here, and I was able to derive that it is in fact 1.1 Kelvin per watt, so fairly close to that sort of rough figure that I was using before. So that also illustrates the really bad effect for Peltiers, that you can see there from the curves there that it is decaying quite quickly, so that leakage effect is quite significant. So that's the end of the test there, the 5 different phases there. And I think this experiment is not just a cool experiment for looking at the relative nature between the Peltier effect and the I squared R effect, but it also neatly illustrates that previous section there where I introduced the model that has those 3 elements. So each of those 3 elements are seen here independently. You have phase 2, which is your I squared R bit, phase 3, which is your heat pump effect, and then, phase 4. And then phase 5 for that leakage effect there. Normally I run this test for a bit longer and use a precision current source where you get what I call this bent tuning fork curve. So at the start of the test here, you see the wonderful Peltier effect. The temperatures diverge really quickly, and I can analyze that to figure out what the QC is there at the start, and then I can find a ratio between that QC and the current that I'm using. Over the long term, though, it sets up a constant temperature difference between the hot and cold sides, and this is because that QC, it's still there, but it's now just circulating through that internal resistance. And because we know the QC, we know the temperature difference, we can make an estimate of that internal resistance. The reason why the curve kind of bends up slowly there, that's just the I squared R losses that are still gently heating the system over that longer term. So that's basically it. This is, as I say, I think it's a pretty cool experiment and also useful for deriving the parameters of a Peltier, so you could compare a good quality one versus a cheap Amazon one. All right, time to finish it there and move on to the next section. Okay, it's time to get back into the classroom again, and I'm going to throw all the formulas that I want to talk about on the screen here as a little bit of a shock value, but don't worry, it's not as bad as it looks. So the first three formulas are the main ones I want to cover, and they're not too complicated, as we will see. The other two formulas are more to do with, if you'll find them if you do any research about heat pumps and Peltiers, and they are a major source of confusion. So I need to at least tell you what they kind of represent. Okay, but anyway, the first equation I want to cover here is the QC. This is the cooling power that comes out from the cold side of the Peltier, and the formula for this is QC equals alpha Ti minus a half I squared R minus K dt. Now, in fact, these three components here are the same ones that we've already been discussing in the original model and also the experiment that we just did. So they're not particularly complicated. So the first one there is your alpha Ti. That is this wonderful Peltier heat pump effect there. The alpha is a kind of coefficient that changes with the different types of materials that you're using. Like if you're going to use copper and aluminium as your Peltier, there were very low alpha for that. Semiconductors, of course, a lot higher values, but it's going to change depending on the chemistry. So that alpha gets multiplied by the temperature, but that temperature is in Kelvin, so it's around 300 for room temperature. It doesn't change very much. So you can put those two together, alpha T, and come up with a number. For this particular Peltier here, it turns out to be around 23 watts per amp. I think that's the actual value for 27 degrees. The next factor is the I squared R, the joule heating, which has to come through and somehow appear in the equations, and you get that half factor there because, as we said, it's going to split between the cold side and the hot side. So it makes sense. And then the final factor, the resistance in that I squared R. It does depend on temperature, but it doesn't change that much. So the actual datasheet value for this guy here is 2.35. I might use 2.5 just to, again, give myself a little bit of a margin there. But again, it's not going to change very much. And then the last factor is just that leakage between the hot and cold sides. One difference is that the formula here, this is the one you'll find in literature, has, conductance, whereas I prefer thermal resistance. So conductance is in watts per Kelvin. Thermal resistance, it's the inverse, Kelvin per watt. Anyway, it turns out this guy here is 1.1 Kelvin per watt. Again, round it down to, say, 1 Kelvin per watt for a little bit of margin. And then the inverse of 1 is 1, so it doesn't actually matter. But for other Peltiers, it may be important to keep in mind whether you're talking about conductance or thermal resistance. Okay, so that's it. That's the three elements of the QC equation. Nothing special there. Now the power in that goes into the Peltier, this is the electrical power into it. It is going to be, of course, that I squared R, but you will also get the effect of that, the voltage that gets generated if there is a temperature difference between the hot and cold side. So the current has to push against that. So there's a component there, 2 alpha dt times the current will give you that effective power there. So, and again, sometimes that's not very much, but sometimes it can almost double the apparent power there. Okay, so that's it. They're the two equations. That's all you need to describe how Peltiers work. Now, if you want to do the COP, just divide the QC divided by that power. If you do have a DT, I wouldn't try and simplify that at all. Just, we've got Excel sheets and stuff, calculators and things, and it doesn't make sense to try and simplify it. However, if you do have a DT of 0, it does simplify down to something quite nice. It turns out that it's the COP equals alpha T divided by Ri minus 0.5, and that alpha T and R are all kind of constant around room temperature, so it ends up just being roughly speaking, a constant divided by the current minus 0.5. And you can see that this is going to have this 1 on X kind of shape that I've been talking about and what I've been actually measuring in real world systems. So it's there, it's in the maths, and it's a kind of this amazing effect. So that's basically it for the formulas you do need to know. Now, if you have a DT of 0, of course, the equation is very simple. If you do have a DT, say, of 10 degrees, you can see on the data sheet here for a DT of 10, you get this curve which kind of peaks at a point and then goes back down again. And you might want to ask a question, well, how do I calculate that peak, the peak COP? Maybe I want to adjust my experiment to get exactly at that point. And there is a way to do it that would involve, say, taking the derivative of the COP with respect to current, equating that to 0, solving for the current, and then plugging that back into your COP equation, and you'll get that number. So there's a bit of a maths involved there, can be done. Now, what the people did maybe 50, 60 years ago when they were playing around with Peltiers at first, they developed this figure of a ZT figure. So this is alpha squared times T divided by the resistance and divided by Kelvin. Now you'll find different versions of this formula for the bulk material. The one that I'm giving you here is for an actual production level Peltier, but it's the same concept. So with that formula, you can kind of get a quality sense of the material, because on the top is the good stuff and on the bottom is the negative stuff. So if you can maximize that number, it will tell you that you've got a better material. So, and obviously they've gone to look for the best materials that will give you that ZT. And then you can also use that number to calculate the maximum COP. So there's a kind of bigger long formula. I'll put it up on the screen, and you can, you'll get exactly the same result that I just gave you without going through that complicated maths there. It's all built into it. So that's basically what is occurring when people talk about the ZT numbers. Number one, you have the ZT itself, which is the quality of the material, and then you can also plug it into this bigger formula to work out the COP. Right, there is one more formula I wanted to introduce, which is the maximum COP based on the Carnot theory. So this is based on the fact that entropy must always increase, I think, if I understand correctly. This is your second law of thermodynamics, and from that you can derive that the maximum COP for a heat pump is going to be something like the temperature of the cold side divided by the temperature difference. It's a very simple formula, and this is like the universe's speed limit for the maximum you can get out of a heat pump. The interesting thing is that not only will that apply, it definitely applies to Peltiers, but you see it appear there in that ZT equation for the maximum COP. So there appears to be something related between the that second law of thermodynamics and the ZT and the COP max there. So it also has a slight problem, is that if you have a DT of 0, both of those formulas blow up. They give you an infinite value. So that suggests that there's something strange there. And also, if you have a negative DT, maybe your heat pump is pushing in the same direction as the natural heat flow, those formulas give you negative COPs, which is kind of crazy. So there's a few things that are wrong there. So obviously we'll be dealing with those things in the next video. But that's basically it. That's all I want to do for the formulas here. Next, I'll just wrap this video up and give you a little bit of a lead into the next one. All right, I'll leave it there. So we've got to the end of the video here. I want to close out by listing off 3 problems that I have with the material that we've covered so far. And the first of these is the poor reputation that Peltiers have due to that low thermal resistance. I didn't really talk too much about the I squared R, but keep in mind that the current that we used in that experiment was only 350 milliamps, and normally we'd be using, say, 10 times that. We're going to get 100 times the I squared R losses, so it might be 30 watts, and that's really going to kill the performance. And yet somehow I'm getting good results out of my system, so there's a disconnect there that doesn't make sense. So that'll be addressed in the next video. The next problem is this ZT equations as well as the Carnot theory. Both of those are blowing up at a DT of 0, and they can't handle negative temperatures, whereas heat pumps are quite happy to work with a DT of 0 or even with the flow of the natural temperature difference there. So something's wrong there. And then the final one is just this DT, not DT, the COP of 30. Really, what does it mean? Yes, we've gone through the formulas and they match the experimental results, and the data sheets also show the same curves. So it all lines up, but we still haven't explained how do you get 30 watts of cooling with just 1 watt input. It just doesn't seem to compute, so we need to go into the molecular level to explain what's going on there. So that's it for this video. I did end up spending 2 days recording what we've covered so far, and it has blown out to 35 minutes. I just don't seem to be able to get these videos down on the time, but hopefully you've enjoyed it. If you do have any comments, please put them down there. I will reply to those. But anyway, it's Friday night. I want to have a beer. I will get on to the next video next week. For now, hope you enjoyed it, and I will see you later.